Hello and welcome to July 23rd, 2021, July's webinar from PJLA. My name is Michael Kramer. I am the Calibration Inspection Program Manager at Perry Johnson Laboratory Accreditation. And today's webinar will focus on PJLA's policy number 3, PL3, which is on our policy on measurement uncertainty. As always, this webinar is being recorded. I realize it's a Friday afternoon. Perhaps some folks got off to a early weekend, so not to fear. Shortly after this broadcast, this webinar will be available on the PJLA website. Also, for those folks who just would like the slides, you can also request those as well. The duration of this webinar is set. It should be no longer than an hour. Questions, again, as I always say, please keep your questions in regards to, excuse me, today's topic, which is the requirement specified in PL3. You should have a space there provided to you for you to write questions if they come up. And at the concluding of today's webinar, I can go back and retrieve what's been sent in. All right, update notification number 55 was sent out by PJLA's headquarters on April 2nd. And we did revisions to our policies, and then you can see right there, PL3 was incorporated into those revisions. So going to highlight a lot of those changes today. A lot of changes came about because the requirements in 17025 changed with the revision from 2005 to 2017 concerning measurement uncertainty. Okay, the requirement to estimate the CMC, we'll refer to it as CMC, however, that stands for calibration and measurement capabilities, used to be referred to as BMCs, best measurement and capabilities, applies to calibration organizations only. This policy is based on the requirements, of course, that's outlined in ISO 17025, ISO 15189, which is for medical labs, ISO 17034, reference material producers, 17011, that's the standard that PJLA adheres to, and then ILAC P14, which you see the P under in regards to ILAC, that's a policy document. Hence, their policies become our policies, and those requirements are incorporated into, in this particular case, the requirements from P14 are brought forth into our PL3. So, applies to calibration labs and test labs, which an accredited results is to be reported. In accordance to ILAC P15, as always, even prior to the revision, will be required to determine measurement uncertainty in accordance with the GUM. They have heard that term. That refers to the Guide to the Expression of Uncertainty in Measurement. So the CMC, calibration and measurement capability, is an effort to express the smallest uncertainty which an organization can attain when performing a more or less routine calibration of a nearly ideal device under nearly ideal conditions. Accredited calibration labs shall not report smaller measurement uncertainty than the uncertainty described by the CMC for which a laboratory is accredited for. So we'll go in a little bit more detail on that, but that is a requirement that if you're reporting measurement uncertainty, that it should never be less than your CMC, which is the uncertainty that's reported on your scope of accreditation. Accredited organization shall identify the contributors to measurement uncertainties, When evaluating measurement uncertainty, all contributors that are of significance, including those that are arising from sampling, shall be taken into account using appropriate method of analysis. The organization must estimate the CMC for every measured quantity, instrument, or gauge listed on its desired scope in accordance with its documented procedure. The organization shall then prepare an uncertainty budget containing all relevant information related to the identified significant resources of uncertainty. So I could tell you, particularly with folks that are just, say, going through their initial accreditation, my experience as a calibration assessor is uncertainty budgets. They seem to be one of the pitfalls or some of the more difficult challenges I find organizations that has not had to work with uncertainties, look at them, develop uncertainty budgets, develop an understanding of them, will struggle with. Not all the time, but I would say that's probably one of the top three items for initial organizations that I personally have assessed on initial accreditations. So basically, when we're doing an uncertainty budget, we are following the following steps. We have to identify the measurement, the contributors. So ideally, you want to make a list of all equipment or conditions that diminish the correctness of the measurement uncertainty. Step number 2 is the quantification. So you have to develop for each one of those significant contributors, you have to assign it a value, reasonable value for the standard uncertainty of each identified contributor. Step number 3, you have them, you quantify them, and I'm sort of going over quantified pretty quickly here, but that's very important. It's quantified correctly. You have an understanding of the distributors and how that's incorporated into this equation that we're listed down at the bottom here, or excuse me, for step number 3, which is you have your contributors, you quantify them, then you have to combine them, and that's the equation for a combined uncertainty. I call it the root sum squared equation. Once they're all combined, then finally we expand the uncertainty, which is basically multiplying it by the appropriate coverage factor to obtain the expanded uncertainty, which is typically a K factor. In almost all cases, I see that at K equals 2 or a 95% confidence interval. So with any uncertainty, when I start trying to go over uncertainties with an organization, you should always consider in your uncertainty budgets these 3 items. The reference standard. So this is the standard, your equipment, where you're receiving your traceability, when you're comparing a known to an unknown. This is where you send your standards, your equipment off to have calibrated. They should have an uncertainty associated with it. So if you think about it, that's where the link of traceability begins for you. So each time you get a little bit further away from the SI through NIST for us here in the US, that chain, that link of traceability becomes a little bit bigger due to measurement uncertainty, because you're going to build on that reference standard uncertainty. Uncertainty should always have a repeatability associated. We'll talk about that here in a little bit more. And resolution. So we always have a uncertainty associated with the limited resolution of the instrument that's being calibrated. From there, it basically depends on the type of calibration as to what contributors need to be considered. Each specifically will include specifications or drift associated with equipment, environmental effects, temperature, humidity, barometric pressure, coefficient of thermal expansion, physical constant and conversion factors, and metrologist effects. Some things that I as an assessor would tend to be looking for, and bear in mind With 17025, the folks that we send out to do assessments are going to be technically competent in the area. So beyond those big three of standard, repeatability, and resolution, going to have a pretty good idea about other things that should be included in an uncertainty budget. For a pipette, for example, I would need to see temperature on an uncertainty budget. You're converting from a mass to a liquid and converting it to a set temperature. Also, ideally, humidity effects that's calculated in there. For any mass calibration, if you're doing precision mass, you have airborne effects, and what's taken into account in coming up with that is contributors with temperature, humidity, and barometric pressure. Electronic types of calibration should always be looking at drift with a standard. Typically, from calibration to calibration, your electronic standards may tend to drift. That can be captured in the manufacturer specs. After a period of time, if you look at the history, you may have enough to justify perhaps lowering that uncertainty. Any sort of dimensional type of calibration, such as gauge blocks, micrometer, calipers, typically would be looking for uncertainty associated with thermal expansion and the effect that the uncertainty that has on the different types of material that's being calibrated. Thermometers via liquid bath. Typically, you'd want to look also at the uniformity of the bath. IR temperature, using that black body, looking at the influence of emissivity. Hopefully I said that correctly. So uncertainty, we have type A, type B. Type A contributors are those that you have statistical data used. And like I said, you're always looking for uncertainty associated with repeatability. That is typically a type A type measurement, which is typically your standard deviation of repeated measurements, preferably at least 10 for that K, getting close to that 95%, or T distribution of 2. Type B contributors, these are contributors to uncertainty that you have no statistical data for, such as those you get from manufacturer specs or using professional judgment or capturing off the calibration certificate. So again, I'm going to emphasize this, that when you for the calibration labs, the budget to estimate the CNC for inclusion on your desired scope of accreditation, your organization shall consider the performance of the best existing device available for each calibration discipline. This means that for sources which can be expected to vary from calibration to calibration, identify the smallest contributor which will occur when the conditions occur. Which calls it, and optimize and uses those values to estimate the CMC. Because remember, you can never report an actual uncertainty which is less than the stated CMC on the scopes of accreditation. Each calibration should have an independent uncertainty associated. One thing I like to sort of stress here, when you the best existing device. For example, if you're doing temperature and your standard reads to 0.001 degrees C, got 3 decimal places there. You want to look at the best device that you can possibly calibrate. You're not going to be able to calibrate, ideally, nothing with the as fine a resolution that of your standard. You'd be performing an injustice to your customer as far as a 1-to-1 ratio there. So you might want to consider in your CMCs, you want to be probably about 10 times better, 10-to-1, perhaps under that source of uncertainty contributor, resolution of the device under test. The best you're going to do would be 0.01 degrees C. Hence, if you happen, that would be on your scope of accreditation. If perhaps you're calibrating something on whole degrees, that actual uncertainty would actually be higher than what's on your CMC. Just bear in mind, as stated on the bottom there, you can never report an actual uncertainty less than what's stated on your scope of accreditation. have a couple examples of uncertainty budgets, typical things that we'd see here. Again, I got a pipette here, and for each one of these samples, you're going to see. One thing I want to just go over here is your basic distributions of the big three, which I'll refer to as standard uncertainty, resolution, and repeatability. They are always on an uncertainty budget. So if they're not quantified correctly, you're going to have an error in your total uncertainty. So on each one of these budgets I'm showing here, for all the uncertainty associated with a standard, that is typically a normal divided by 2. That comes off the calibration report. That is the K factor because it's already been multiplied by 2. So that would be the uncertainty divided by 2. For your repeatability, the uncertainty associated with that should always be considered a normal distribution. So in other words, 95% of the values should fall between 2 standard deviations around the mean. The divisor from that under a normal distribution, it is what it is, divided by 1. So whatever that standard uncertainty is just the divisor of 1. Other ones, such as resolution of the device being tested, gave the example of a thermometer. The smallest increment you can read on that is 0.01 degrees C. That is considered a rectangular. That stays the same throughout the entire range of that distribution. And that should always be a divisor of standard uncertainty over the square root of 3 or divided by 1.73. A good rule of thumb I like to pass on, if you're not sure what the uncertainty beyond those 3 that I just mentioned, you're always more or less, it's a safe bet to assume it's a rectangular type of distribution. Here we have a power tool, just as perhaps a torque wrench type of calibration. Typical uncertainties we can see here. We got the 3 there, and we have some additional ones that were determined, such as joint rate simulator additions, manufacturer specs as a drift with the instrument, electrical simulation, electrical type of calibration. Again, we have 3 items there that are always on there. Some of them also includes not just the uncertainty associated with the unit under test, but I'm not a stickler for actually looking for the uncertainty of the actual standard that's being used, but there is an uncertainty associated with that. It's up to you to make the determination to include it in your budget. If it is a significant contributor, then by all means include it. And there's plenty of resources that can do the magic for you. In other words, when I say that, I mean the calculations, that root sum squared, where your true job, of course, is identifying, and then you have to quantify, hopefully come up with the correct distribution, and let the spreadsheet do the math for you. That root sum squared, combine them, multiply it times 2 to expand it. All right, one rule of thumb, it's always been in PL3, still is that an actual uncertainty, as in your scope of accreditation, and also being reported on your reports that you're reporting to your customers, shall be, that's a requirement, shall be no more than 2 significant digits. So we have more information on that in PL4. We go over the general rules of rounding. But typically it makes it a point to pretty much to round up all the time. Have some examples down there as what would be considered 2 significant digits if you actually calculated a uncertainty of 0.149, for example. It's non-conformance as per PL3. To report that like that on the calibration report you're putting out, you would have to reduce that to 0.15. And for those of you who are interested, and I utilize it myself, we have on our website a calculator that will round to 2 significant digits for you, following the rules of rounding that we have specified in PL number 4. The uncertainty covered by the CMC shall be expressed as the expanded uncertainty having a coverage probability of approximately 95%. The unit of uncertainty shall always be the same as the measured, and in terms of relatives to the measures, percents, or perhaps per unit per whole unit. That requirement's always been there. However, an addition's been brought forth in in P14. Of course, we brought forth to that policy to PL3 as the usage of ppm, or such as parts per million, parts per billion. Because of the ambiguity of definitions, those terms are not acceptable. That's an addition to that we've added when we revised PL3. PL3 also addresses in-house calibration, and in a nutshell, the same requirements apply for in-house calibration as far as having uncertainty budgets, calculating uncertainty. If you're not aware of what I'm referring to for an in-house calibration, if you're a test lab out there, and let's say you have pipettes and you decide, hey, we're going to calibrate these ourselves. And as a PJLA, I'm just talking about uncertainty here, but that would be assessed just like a accredited type of calibration, which means you have to have the appropriate procedure. And part of the puzzle is you have to have the uncertainty. By the definition of traceability, traceability is needed, then the definition incorporates the measurement uncertainty. Testing labs. I'm just talking a lot about calibration. Just want you testing folks to know that this is not an area you can ignore. Uncertainty does apply to you. The trick here is you got to find out what bucket your uncertainty would fall in. So you see the requirement there that comes right out of 17025. A laboratory performing testing shall evaluate uncertainty, where the test method precludes rigorous evaluation of measurement uncertainty. An estimation shall be made based on an understanding of the theoretical principles or practical experience of the performance of the method. So when rigorous mathematical, and this is in PL3, but these are based on the notes that are in 17025. When rigorous mathematical and statistical valid estimation of the measurement uncertainty may not be possible, so the requirements in 17025, that clause I just read up top, would apply. In such cases, the organization must identify all components of uncertainty and make a reasonable estimation. The reasonable estimation is to be based on knowledge of the performance, the method, and on the measurement. I realize quite a few testing labs may also fall into this bucket. In those cases where a well-recognized test method limits to the value of the major sources of uncertainty of measurement and specifies the form of presentation of calculated results, the organization is considered to have satisfied 763 or ISO 15189 for anyone who is accredited to our medical standard by following the test method. Examples such as ASTM, AOAC, and the rest that I have listed there, which included the USP, have methods that would fall into this bucket. Other examples would include rapid method kits that specify limits to the values of major sources, contributors to the uncertainty, as well as well-recognized rapid methods where kits are used to determine qualitative results. For example, a semi-qualitative kit assay that performs qualitative results such as presence or absence based on a numeric value. As a general rule, qualitative or semi-qualitative tests or tests that require personal judgments will not incorporate uncertainty. So in other words, if these are black or it's white, it's yes or it's no. There's no qualitative type of result. Okay, uncertainty is not a one-time thing here. So upon achieving uncertainty, the budgets and decisions regarding sources of uncertainty shall be periodically reviewed and updated by organizations to reflect changes in the organization's equipment, procedures, personnel that may influence the ability of the organization to perform specific calibration or under test under the scopes. These changes shall be documented. In other words, preparing your uncertainty budget would need to be reevaluated. One thing you would always look at would be the uncertainty associated with a standard. So when you send your standard out, you receive it. Two things I always looked at. First of all, I wanted to make sure the device was in tolerance, because if it wasn't, then I'd have to follow the protocol for non-conforming calibration. And then secondly, I would look at that uncertainty. See if it changed from the last time, because if it has changed, then my uncertainty would change. If you moved into a facility, if the location moved, the environment changed, then that would need to be reevaluated, i.e. perhaps duplicate your repeatability studies where you establish the CMC for repeated measurements. So with 17025, when it was revised in 2017, there was some significant changes there in regards to measurement uncertainty. Hence, that was brought forth into PL3. So under 17025, under reporting, requires calibrations to report the measurement uncertainty of the results presented in the same unit as that in terms of the relative measured. So if you recall back before what the standard was revised, it stated you shall report the uncertainty and or a statement of compliance. The and or has gone away. So our prior to this copy of updated the PL3, our previous one went into a lot of dissertation about if you did not report uncertainty, what had to happen. Well, considering the standard now requires it, we did away with all that dissertation. The only way as far as not reporting uncertainty would be permissible would come under the realm of simplified reporting. And in that case, and we specify this in PL3, well, first and foremost, this should be customer driven and not the CAB or lab driven. But it was only permissible if agreed to by the customer during the contract review process, and this agreement shall be documented. So there is the requirement now in 17025. You see the word shall. You shall report uncertainty, and the and or has gone away. Okay, decision rule. So this is a new definition brought forth in the 2017 standard. Hence, we are addressing it in PL3. So decision rule is how you take measurement uncertainty into account when you make statements of compliance. So it comes up twice in 17025. It comes during contract review. So as required in clause 713, customer has to agree to your decision rule, which will be employed when making statements of compliance. The decision rule is defined as a rule that describes how measurement is accounted for when stating conformity with a specified requirement. If a statement of compliance is being made on calibration reports, the agreed decision rule is required per 781 to be documented on the report. So hence uncertainty. If you're making a statement of compliance on that report, in other words, when I say that, you're saying something passes, something is in tolerance, out of tolerance. You're making a statement of compliance, hence the decision rule shall be documented on the report. Even if you have simplified reporting and your customer agreed to not have uncertainty on the report, like I said, that should be customer driven, that the decision rule would still need to be specified if you're making a statement of compliance. I did believe if you want to go back on and recorded webinars, we've given a presentation on statement of compliances and decision rules. Talked a lot about the ILAC guidance document G8, which we referenced this as in PL4 as guidance in determining and selecting the appropriate decision rules. So again, just to sort of visualize it here, we're referring to taking uncertainty into account and making statements of compliance. So if we look at the top chart there where it says upper specification, that line is a tolerance line. The value at the very top is clearly out of tolerance. Both the value, which is the dot, and the lines with the end caps there, that would be considered the measurement uncertainty. Both are clearly out of tolerance. Hence, regardless of whether or not we take measurement and uncertainty into account, it's going to fail or not meet the upper specification. Next one down. I had a little pointer here. I hope folks are seeing. I don't know if you can see my mouse or not, but I'm pointing up to the middle one up there on the upper specification. On that one there, we see the value that's clearly out. We have the surrounding uncertainty, which creeps into the past. So we could possibly, if we're not taking uncertainty into account, just going by that value, we would say it failed. But there's a gray area there because it may not fail because of measurement uncertainty. And then the next one down, I'm going from right to left, by the way. I should have clarified that. We have the value below the spec, so that value passes. However, there could be the possibility of false acceptance there because the uncertainty may not pass because of uncertainty there. And then last but not least, far left, under the upper specs, we have both the value and the uncertainty clearly within the realm. Hence, we can clearly state that passes. Typically, when you're taking measurement uncertainty, it refers to some sort of guard banding, where you're guard banding and you're going to red flag anything in which uncertainty would affect your statement of compliance. So again, that ILAC document goes everything from guard banding to simple acceptance, which is something where you don't take measurement uncertainty into account. That is a valid decision rule. However, your customer again has to agree to it, and the risk of false acceptance in those cases can be up to 50%. And I'll leave that up there for a second, but ILAC G8 is available online from the ILAC website. There's the web address, or just Google ILAC G documents and you can find it. Not just this one, but all the documents. If you're interested in P documents, you can Google and find the policy documents as well. Okay, just looking at PL3, we had a couple other slight revisions. We made some modifications to include appropriate requirements and references to RMPs, folks, for reference material producers, and additional source for your medical labs. We added there, which I list there. And we have sections dealing with some requirements concerning reference materials, which is section 7.0, and section 8.0 is medical labs, 15189. Okay, thank you very much. That covered a lot of ground there over a relatively short period of time. So bear with me a moment. Okay, bear with me. I'm trying to capture the questions here. And I'm reading this as advertised with the new version of the gum. Didn't realize that. 6 of 2020, do we need to update the existing uncertainty? Again, I'll resort to what we stated in PL3. If anything's changed, such as your environment, your standard, then of course you have changed. But I don't know. I am unaware of anything that's specifically stated in the gum, and I'm not an all-around expert. You may know something that I don't know that says you have to consider another source there. I'm trying to digest this next question. And I'm not really sure if I'm answering your question correctly. I don't know if I really understand. A laboratory can express a statement of conformity based on a standard. Correct. You can have tolerances based on a standard, or method statement, or define limits of standard. I don't really understand myself limits of the standard. I know it's very specific. Statements of conformity can be based on many things. It could come from a standard. What comes to mind would be for say test weights, precision test weights. You have ASTM E617. They go from 1 through 6 with specific tolerance on there. One being the smallest, 6 being the largest. You can also have customer specified tolerances, or which for example, if your customer has a reason to have a larger tolerance, for example, when I was on a calibrator, I remember an organization calling me and saying, "Why do we have so many failures?" And I would say, "Well, you're stating manufacturer specs. Oftentimes, manufacturer specs could be a selling point. In ideal conditions, on no worn parts or so they could be relatively small." I explained that, and they said that's how small. Well, that doesn't that's not going to affect us. Well, you could do your own research and determine how far they can be off. A card could possibly determine whether or not that is going to affect the testing. So statements of compliance can be based on a lot of things. The main thing is you want to meet your customers' requirements. So if and often they may not know you're an accredited organization, and they may very well depend on your guidance in that. Where can we locate the video? www.pjlabs.com. We have a tab there that specifically says webinar. And then one of the drop-down boxes would be recorded webinars. Feel free. I'm not sure if it's going to be available right after this. It might take a little time. I would say by early next week. Yes, if you had a colleague that hopefully missed it and would want to go back and listen to this. And I'm a calibration person, And I don't know all areas of calibration. I am not a testing person at all, so I'm not going to answer the question about bacteria because, quite frankly, I don't know. I'm not versed in that area of testing. But the question is how and if somebody knows the answer, Pat, you can type it in your block. How would you express uncertainty if you are growing or trying to grow bacteria to see if it is present? The only thing I'm not familiar with the test, but if it's a yes, no, you're not quantifying it, then you really don't need uncertainty. That was specified earlier in the presentation. But if you're going to give it a numeric value, then I would say a reasonable estimation would need to be made. See if I get any response from the gallery out there. Does anybody else, would anybody else know? All right, bear with me 1 minute. Got myself. All right, got some response to the question we were answering before. As a microbiology laboratory, we use a lot of USDA, FDA protocols. So would we need to find the uncertainty they ascribes to the protocol? I'm sorry, I thought you were answering that question. I would say I don't. Again, if it's one of those methods where it basically highlights the sources of uncertainty and gives limits to them. For example, I'll refer to a balance. Again, if it's specific and it says you need to use a balance with at least 4 decimal places, 0.0001 or 1/10 of a milligram, then I would say that would fall into that bucket. And then again, I don't do those sorts of testing. I'll give you all. I thought we had it. I must did away with it at the first part of the slides for where you could submit questions. But if you would like to bring those questions forth, and actually, there's no need to do that because we do capture them at our headquarters. I will present them at PJLA and hopefully have somebody to get back to you on those. I don't like to leave. I don't like to be unsure when I give an answer like that, but I'm sure in our brain trust at PJLA we can get a more direct answer for you. And Kristen, if you're listening to me, yes, if you could send me the list of questions that were typed in here. I wish I had a testing person online with me to answer those questions. All right, that's it for the questions. Good questions. Uncertainty is one of those things that we do haven't done one in a while, but we used to give workshops on it. And it's not like one shoe fits all. You can do basic uncertainty, but everybody's really would like to know what's pertaining to their labs. There's, uncertainty. Like I said, for calibration, you're going to look at those first 3, and then from there it depends on the type of calibration that is going to be incorporated into it. So what's next? The next webinar, which we have a little break here all the way till the end of next month, August 30th. And we are going to look at corrective action. Something that one of my favorite topics, corrective action, determining the root cause, taking corrective action to address the root cause, hence preventing its reoccurrence. So thank you all for signing in here. and I look forward to presenting and hopefully having you all log in next month. Thank you very much.